Hi, welcome back. So before the air break, we were doing all the proofs of the three theorems, of the three rules, sine rule, area rule, and cos rule. Okay, so we're going to start off with doing some examples now with applications of all three rules. But specifically, today we're going to focus on those examples that require us to use variables. There's no numbers in it, there's variables. They haven't given us the values of the angles and the sides, but they've given us variables, and we need to write out formulas in terms of variables or the lengths of sides or angles in terms of certain variables. So let's begin. Okay, before we start, let's quickly revise how we decide which rule we're going to use. So we've done this a few times before. You should be very familiar with this. So the first thing we look at is the triangle right angled? If it is, then we ask, does it have angles? If it does have angles, then we go to grade 10 trigonometry using the three ratios, sine, cos, and tan. If it doesn't involve angles and it's a right angle triangle, then we probably have to use theorem of Pythagoras to find the sides. And the grade 11 part is if the triangle is not right angle, the first question we ask, do we have one full pair of angles and a matching, one full pair, that means an angle and its opposite side, so are we given that? And if we're given that, then that means use the sine rule. And remember again, the sine rule is used when we have angle, angle, side, or side, side, angle, but not an included angle. Okay, but if we don't have one full pair of angles and sides, then we know we're probably going to be using the cosine rule. And the cosine rule, if you want another way to remember when to use it, we use it when we have side, angle, side, or when we have three sides and we want to find an angle. Remember here we're kind of looking for a V pattern. Okay, so let's begin with our first example. Okay, in this figure they've given us a triangle XYZ with y is equal to theta, so they've given us this angle here, and they've given us these two sides xy and yz which are equal, and they both equal to b. Okay, and they want us to show that xz is equal to some expression, this expression here. Okay, so what we have to look at again, we're going to check our rules. Is it right angled? No, it's not right angled. Do we have one full pair? As it stands, we don't have a full pair. We definitely don't have an angle and a matching side. But what we do have, which means we're probably going to use the cos rule. So let's check to see if we have exactly what we need for the cos rule. So remember, when we're looking for the cos rule, we need to have a side, angle, side. So do we have a side, an included angle, and another side? Yes, we do. So we've checked all three boxes for our cos rule. So where are we going to begin? We're going to start off by writing out an expression for xz, because that's what they want us to do. And we know if we use the cos rule, if we're finding an expression for xz, then we can use the v across from it. So we can use this side, the angle in between, which is that one, and the side adjacent to that angle to find the value of xz. So let's begin by writing that expression. Okay, so we decided that we don't have one full pair, okay, just to double check where we started off. So in other words, we can now write an expression for xz. So xz squared will equal to that side squared, so it's b squared, okay, plus the other side, so it's going to be another b squared from that way, okay, minus 2 that side, so it's going to be b, and we're going to say cos of the angle across from xz, and the angle across from xz is theta. Okay, so basically we're saying xz squared is equal to xy squared plus yz squared minus 2 times xy times yz times cos of the angle in between, which is theta. Okay, so that's what we had written on the previous slide. This is just a neater version. So now we're just going to do some algebra to kind of neaten this up and see where we end up. Remember, we're looking to find xz. What we have on the board at the moment is xz squared. So we begin by just adding b squared plus b squared to give us 2b squared. we multiply out these two b, and we end up with another b squared. And now you'll notice we can see what? It's quite obvious to see there's going to be a common factor. Our common factor, we've got a 2b squared here, and we've got a 2b squared here, so we're going to factor out the 2b squared. Okay, so what will we be left with here? From the first term, we're going to be left with 1 minus, and from the second term, we've taken out the 2b squared, we're just going to be left with cos of theta. Let me just get rid of this. Okay, now remember, we're not looking for xz squared, we are looking for xz. So we have to find the square root of this whole right-hand side. So let's find the square root of the right-hand side. Okay, so if we find the square root of the right-hand side, we're going to put everything under the square root. So it will be 2b squared into 1 minus cos of theta. Now, if you look at this expression, I could take this b squared out of the square root, and what will I be left with? It will come out of the square root, and then the square root of b squared is simply b. So if I just write that out now, I'm going to end up with that b coming out here, and I'm going to be left with 2 and the bracket, which is 1 minus cos of theta. Let's go back and see what they asked us to prove. They wanted us to prove this. They wanted us to prove that xz is equal to b square root 2 brackets 1 minus cos theta, and that's exactly what we've proved. Okay, so it does get a little tricky when there's variables instead of numbers, or lengths of angles, lengths of sides at angles. But eventually, if you apply the rules in the order that we do, it'll make it a bit more easier for you to decide which rule you need to apply. Let's try another example. Okay, so George stares at the point G, a distance from the vertical office tower at AT, and he sees Nandi at the window at n meters from the top of the building, so that's that height. And the angle of elevation from George to A is alpha, so this big angle here is alpha, that one's alpha. And the angle of elevation from George to Nandi is beta, which is that angle there. Okay, and they ask us to express G1 in terms of alpha and beta, and then they ask us to express A in terms of alpha and or beta. Okay, let's go and examine this diagram quickly. Okay, so they want us to find G1, this angle here, this small piece here. Now, the whole angle here is alpha, okay, and this little piece is beta. So obviously, G1 is simply what? It's simply alpha minus beta. And the next question they asked us is to find A. Now, A is in this big triangle here. It's part of the triangle AGT. And in this triangle, we've got A, we have this 90-degree angle, and this angle here, we know is alpha. So, what will A just be? So, because this angle is 90, it means the two remaining angles have to be 90. So, in other words, because alpha plus A had to equal to 90, that means A just had to equal to what? 90 degrees minus alpha. Okay, and how do we know that? From three angles of a triangle, because we already have this 90 and we have alpha here, so A had to be the complement of alpha, which was 90 minus alpha. Okay, we're going to use these two in the next part of our question. Now they ask us something a bit more complicated. They ask us to show that H is equal to n cos alpha sine beta over sine alpha minus beta. Sounds quite complicated, but we know we just need to find an expression for H. Okay, so H belongs to this small triangle here. But if we look at the amount of information that we have on this triangle here, we've got beta and we've got H. So it's easy. It's a right angle triangle. We only need two bits of information and we have them. We've got H and we've got beta. So we can rewrite an expression. We can try and find an expression for sine of beta. And sine of beta will be opposite over hypotenuse. So it's going to be H, and the hypotenuse in that case was Gn. Now, we're going to rearrange that. So we make h the subject of the formula, just multiply throughout by gn. So we're going to get h is equal to gn times sine of beta. Right. Now we're going to be using sine rule in triangle AGN. So in triangle AGN, we already know that gn, okay, we're going to use sine rule. So we're going to use gn and the angle across it. And can you remember earlier we said this angle was 90 minus alpha. So in other words, gn over the sine of the angle across it, so sine of 90 minus alpha, is equal to, and we're going to use the other side that we have, and the other side that we have an expression for is going to be an, or it's going to be this across and the angle across it. So it's going to be n and sine of the angle across it. And across from n, we had g1. And remember, what was the sine of g1? I mean, what was we found g1 to be earlier? g1 was, can you remember? It was that big angle minus the small angle. This is what g1 was. Okay, so we're going to substitute that in here. So we're going to say alpha minus beta. So we've used the sine rule again in this one here. Let me just remind you what we've done. We've said in this triangle AGN, gn over sine of A is equal to an, which is little n, all over sine of g1. And that's the expression that we have here. Okay, so there's a neater version of what we had earlier. Now, we're going to, we have two choices. We can either multiply throughout by sine of 90 minus theta, but what do you notice about sine of 90 minus theta? What does it remind you of? Can you remember? When we did reduction formula, then sine of 90 minus alpha, we got to use the Coco rule, so it becomes cosine, oh sorry, my pen is doing funky things. Okay, it becomes cosine of alpha, okay? And that's from using the reduction rules. I'm not sure if that's how you learned it. A lot of people refer to it as the Coco rule because you find the co-ratio of the complement. So sine of 90 minus theta becomes, sine of 90 minus alpha becomes cos of alpha. Okay, so what I've done first is I've just multiplied first through by sine of 90 minus alpha just to get rid of the denominator on the left-hand side. And now I'm going to change that 90 minus alpha into cos of alpha. Okay, now we have an expression for gn. So now we have an expression for gn. Okay, but remember we were trying to find an expression for h. And earlier we said that h is equal to gn times sine of beta. Okay, sorry, there was just some things I needed to get rid of. Okay, so h is equal to gn sine beta, and now I'm going to substitute this piece here for gn. Okay, so I'm going to put that in place of that gn, and let's see what happens. Okay, so n cos, sorry, it was actually that expression, the simplified version. N cos of alpha over sine of alpha minus beta. Now I'm just going to take this and just neaten this up and multiply this into the numerator here. So we end up with that expression, and that's exactly what they asked us to prove at the beginning. They wanted us to prove that h is equal to n cos alpha sine beta over sine of alpha minus beta. Okay, that brings us to the end of that example. We take a short break. I'll see you after the break.